So our next speaker in the KIPAC in the World series is Edward Young. And Edward did his PhD in physics here, it's at Princeton, and graduated in 2018. And he worked on the spider balloon experiment on cryogenic detectors. Then he came to KIPAC as a postdoc. And I assume you were working with Chalin?
And Zish.
Yeah. And Chalin and Zish. Yep. Okay, great. And he worked on deploying the microwave readout multiplexer on the Keck Observatory at the South Pole, commissioning the BICEP array cryostat at the South Pole as well, and developing a space-compatible microwave multiplexer on a chip for NASA. So, and then he went on directly, right, to CHARM. And he's been at CHARM for 2.5 years. And actually, I came across CHARM a while ago. I was looking, somehow I stumbled across it. Cool. And I know that the char part of CHARM it's char, right? And I think that might come in a little bit.
It's a char farm.
Yeah, a char farm. So it's CHARM. So he's the head of research at CHARM Industrial and is going to talk about carbon dioxide removal through bio-oil sequestration. We really look forward to it.
Thank you for having me here today. Okay, before I get going, I just want to say I'm incredibly honored to be here today. Slack is just a deeply important space to me. This is a photo from the Slack Summer Institute in 1989. That is me. That's my dad, who is right back there. This is today. This is me with my son, who's 10 weeks old, taken today, right? He is, I think, in the room behind here right now because he might be crying. But I grew up here, right? This is like after summer camps, I would at Stanford, my dad would pick me up and I'd play on the fields here. Like any good Nepo baby, this is where I got my first high school job. Afterwards, I went off to graduate school and then I came back to work at KIPAC. So I'm just so honored to be part of this organization. This meant a lot to me, just like as a human being. Cool. So this was taken in 1989. This was taken today. 34 years have gone between these two photos. That's a long time, or maybe not that long at all, depending on who you are. Cool. All right. So a lot has changed, right? The Earth has changed in 34 years. When SSI 1989 happened, the world they actually had a pretty cool year. You can see right there, right? It's actually a little bit, they got some nice weather here, but the world had already heated by about 0.6 C from pre-industrial averages. So typically when people talk about climate change, they ask, how much has the temperature on the Earth risen since before the industrial era? So they typically average from 1850 to 1900. So in 1989, when that first photo was taken, we were about 0.6 C. Today, when we took that photo, well, okay, not quite. This was in June, but it's about almost 1.5, right? 1.5 C. And this year will probably be the first year that global temperature averages will exceed 1.5 C average over the whole year. It's a little bit unfair of a comparison because this is an El Nino year, so we expected it to be higher than average, but this will be the first year that we probably will exceed that number, right? Okay, so like we've heard a lot, you've probably heard a lot, we're trying to keep the world but below 1.5 or 2 C by the end of the century. And we're not making good progress. Okay, so why is it happening? I think everyone in this room knows why. We're emitting a lot of greenhouse gases. This plot starts right when that first photo was taken, 1990, and runs to 2100, right? I probably won't see 2100, but Beckett hopefully will, right? And so this is in living lifetime, right? This is the future that people in this room are going to experience. And so let's just talk really briefly about this, right? So right now we emit about 50 gigatons annually of greenhouse CO2 equivalents, right? So there are other greenhouse gases like methane, but the predominant one is CO2, and we typically normalize everything to the equivalent of CO2. So this is 50 gigatons of CO2e emitted annually. And they started kind of modeling this well in 2010, and here's 2020, just to kind of give you a sense of things. And the pink line, triangle, is what would have happened if in 2010 we did nothing. We did absolutely nothing, right? And so you can see it's horrific. We get to about 4.5 C of warming by the end of the century. Fortunately, in 2010, we actually implemented some policies that are actually being enforced. They're actually doing things, right? And so we actually kind of rolled off this curve. You can actually see we rolled off this curve in the last 10 years. And that's really encouraging, right? Like one thing I try to keep people I want people to be optimistic about our fight against climate change because we can do it, right? And we can actually already see it in this plot. So the orange, the middle one, is what our current policies, kind of the pathway that we're going to be on. And we're going to get about 2.7 C of heating, which is still a lot. That's not a world we want to live in, right? But it is better than the previous one. And then the blue line is the pledges, right? So people, countries promise to do things. These are non-binding, right? So that's why it's kind of, there's no real even projection on it, like no error bar, because like, what does it even mean for someone to pledge something? But let's say we do it, right? We get to about 2.1 C. And then our actual goal pathways are anywhere between 2 and 1.5 C by the end of the century, right? One thing I'll just stop right here and note is that this is the zero line, right? So this is zero emissions, net emissions. And you can see that here it's negative, right? So to get to the 1.5 C pathway, we have to have negative emissions by 2070. So that already tells you that we need carbon dioxide removal, right? Because there's no way, obviously the first thing you want to do is to lower the amount of carbon emissions we have, right? We want to decarbonize heavy industry. We want to electrify our cars, have better batteries, all of these things. That could plausibly, although unlikely, get us to zero total emissions, but you actually need negative, which means you need carbon removal. Okay, this one's a little wonky, but I figured this room could handle it. I don't usually add this plot to this talks, but I think this room can do it. All right, so this is just helpful for me to understand what we actually need to do. So this is a simulation. This is taking a climate model, and is Beckett being loud? Sorry, Beckett. Okay, so this is the zero emission commitment, which is basically a simulation where you follow the nominal pathway of emissions. So basically in this plot, this orange line, and then you say, I'm going to turn off all carbon emissions on a given year. I'm just going to say, in my model, I'm just going to turn off all anthropogenic CO2 emissions. What happens, right? So this tells you kind of a limiting case of like, I don't know how you can't do it, but if you did it, this is what would happen. And they simulated, I think, like 10,000 times. And I think just look at the 50th percentile just to ease your eye, to keep it focused, but they have the other percentiles as well. And they say, okay, if you want to hit 1.5 C by either peak, meaning that anytime in the next 70 some years, like it's going to hit 1.5 C, or maybe more relevantly, the second one, the 2100, what is the temperature in 2100? When do you need to shut off all carbon emissions? When do you need to reach net zero instantly, right? And so you can already see, if you want to avoid a peak temperature of 1.5 C, you need to shut off all carbon emissions next year, right? You need to get to net zero next year. Okay, probably not going to happen. Okay, how about if I want to get it by 2100? So I'm actually going to allow myself to overshoot and then come back down, right? So maybe in 20 years it gets, or 15 years it gets to 1.7 C, and then it comes back down, right? You need to shut off by 2046. That's not that far, right? Can you imagine how we would shut off all carbon emissions by 2046? That seems difficult, right? If you want to do the 2-degree pathway, you have a little more time, right? But 2047 to avoid peak of 2, right? That's hard, right? So that tells you that that sort of gives you an intuition that like on very quick timescales, you need to get to net zero, right? You need to be able to shut down all carbon emissions. Okay, so when you put that all together, what does that mean, right? The IPCC, the Intergovernmental Panel on Climate Change, estimates that we need anywhere between 2 and 20 gigatons annually of carbon dioxide removal, right? It depends kind of on the model you use and how fast we can actually decarbonize other sectors, but that's kind of hand waving the number. And the median number is 6 gigatons per year to get to 2 degrees of heating by 2100. I'm just going to tell you, Charm is the market leader in permanent carbon removals. We're maybe one of 2 market leaders, us and Climeworks. That is our total amount of carbon removal as of yesterday, right? So we've done 6 kilotons over 2 years. They need 6 gigatons annually, right? So you can all do the math of how many orders of magnitude we need to scale this. So how do we get there, right? The DOE, right? The people who fund, I don't know, this, well, at least that space, they've set a goal, right? To say we must be able to get less than $100 a ton CO2 removals by the next decade, right? They published this little plot a few months ago. So it's basically in 10 years, we want to be at $100 a ton. If for context, we sell at a loss for $600 a ton, right? So that's kind of where we are right now. Cool. All right. So how does Charm want to solve this problem, right? What are we doing, right? So what we do is we convert waste biomass, that typically means forestry residue and farming waste, into bio-oil via pyrolysis. I'll unpack that sentence. Forestry residue is basically so right now we're operating in the Sierra Nevadas. So for fire mitigation, Cal Fire will actually go and trim all the underbrush, and then they leave it in these piles. And the way they get rid of it, because it's too expensive to pull it out of there, is they actually wait for a low fire risk day and they light it on fire, right? So it's a control burn, and that releases all the carbon dioxide into the air. It's too expensive for them to truck it out. They will pay people to do it, and no one's bidding, right? But we want it. That is our input. So we take that biomass and we convert it into bio-oil via pyrolysis. And pyrolysis is basically a thermochemical conversion process where you convert any biomaterial into oil. And you just heat it in a no to low oxygen environment, and that forms bio-oil. And in fact, almost every one of you have probably pyrolyzed something before without knowing it. If you have ever put food in your grill and closed the lid on your grill and left it for a little while, and then you open it and there's a greasy film on the top of the lid of your grill, that is pyrolysis, because you've basically choked out the ability for oxygen to get in, and you've broken down biomass into bio-oil. Obviously, we're more efficient than that, but that is fundamentally what we're doing. There's probably 50 megatons, probably 10, maybe 50 megatons of forestry residue in the United States available if you took all of it. So it's actually not getting you to gigatons. The farming waste is actually tremendous. So this is our main pathway, and that is the one we're really targeting is called corn stover. So when you and I buy corn at the supermarket, we eat the corn cob, the kernels, but everything else on the plant is just left on the field to decompose, right? So there's the stalk, the leaves, they have no economic purpose for the most part. So farmers don't want it, but you can take that and pyrolyze it and turn it into bio-oil. Cool. So bio-oil is this really carbon-dense liquid. What do we do with it? Well, we purchase spent oil wells across the United States. The United States has about 10,000 empty oil wells, right? We've been very efficient at removing oil from the ground. We're really good at that. They're just sitting there as dead assets. The people who own these things don't want them because they don't want to have the liability of owning a possibly leaking oil well. It's kind of an eyesore, at least to many people. And so what do? We purchase it, and then we bring our bio-oil and we turn the pump in reverse and pump it back into the oil wells where they came from. And that's it. And this is a permanent carbon removal pathway, right? So the lithology, the underground structure, was obviously well suited for holding oil, right? It held it there for millions of years. So we're just putting it back. Cool. All right, so what's unique about Charm? One thing that we do is we build small mobile pyrolyzers. So people have tried this method before, right? So usually in the terms of bioenergy products, so people generally want to make an oil that they can use to sell for sustainable aviation fuel, or I don't know, just like heating anything, right? And the way that people have tended to do it is they build these massive plants, these like huge pieces of infrastructure. And so what they do is they like write an economic model. They like ask the farmers, how much are you willing to sell your biomass to us for? And the farmers will say $65 a ton, which is about the right number. And then they the people who build it put a bunch of capital into it. They build a system, and then now the farmer is like, I am the only game in town for you to sell you biomass. We're now going to sell it to you at 3 times what we told you, right? Because shipping biomass is very expensive, right? It's big and fluffy, so you need big trucks to make it go big distances, right? And it's just expensive. So this plant actually collapsed after, didn't collapse. It did not economically close after they built it, right? And so they just closed it down. So what we do is we build 10 ton per day mobile plants, so we can operate on the farm edge, and hopefully in the future actually on the farm itself, right? So we will actually attach to the back of a combine harvester and just throw, as you're picking it up off the field, just pyrolyze it. And then you take the bio-oil, which is our product, and ship it. And we're very good at moving oil, right? Like we have so much infrastructure for moving oil. We have thousands of people who have spent their entire lives working on that problem, right? And we know how to do it economically. So one, we can reduce our transportation costs, but we can also bid farmers against each other, right? Like if you say you're going to sell it to me at $60 a ton, I will show up. And if you choose to not sell it to me at that, then I'm going to go to your neighbor, right? And if you don't like that, I'll go down the street, right? So it keeps the economics a lot more sustainable. is there enough biomass, right? So we're talking about a problem that needs to exist at the gigaton scale, right? Like we're not interested in doing kilotons. We're obviously at the kilotons right now, but we're trying to ramp to gigatons, right? So annually in the world, there's about 10 gigatons per year of biomass. And the United States was about 1 gigaton, in just North America, so including Canada, and about 200 megatons per year in just corn stover. So our main product right now. We are, in principle, feedstock agnostic. We can take any biomass, but corn stover is our main target. The other cool thing is, this plot's a little bit hard to see, but basically the blue is there's lots of biomass, and the yellowish is there's not a lot. And you can see it's kind of sort of where you would guess would be, like in the Midwest, right? Like that's kind of where you would guess. That's also where all the oil wells are in the United States. So it's actually, that's just by chance, but it's really nice, right? You can make all your bio oil here, and then you don't have to ship it very far. So that's actually a really nice thing we got lucky with. Okay, cool. So what have we actually done, right? Like I've shown you a lot of plots. So this is our first deployment in Kansas, right? So this is I'm gonna say it's mobile, like in quotes. Like you can see, like there's a lot of infrastructures on the ground. This is a first deployment. This is in Kansas. If you're like me, you had no idea how big a ton of biomass is. That's each one of these is about a ton, right? So that's, you want to process that, and you want to process about 10 of those a day, right? 10 tons a day, right? And so basically, just to kind of orient you, the first skid is the first kind of thing right there is the biomass processing. You take these big bales and you rip them up and you shred them down to a size that you can process, and then you convey it across these little augers, and then this. I can't show you the inside of it because that's where our IP is, but that processes it into bio oil that comes out the end, and then we sequester it. Cool. And then we bring it to another well, also in Kansas, and that's the original well on the right. Pump on the right. The big things you're probably used to seeing. We actually decommissioned that one, and we just brought that tiny little device there, and you can kind of see this thing right here is actually the oil well. The hole into the ground, and we pumped our bio oil into it, and that's it. Right, and so we inject into these salt caverns. This is just kind of a cross-sectional view of a salt cavern. I just think they're really cool, honestly. Oil and gas, again, lots of money. They have these beautiful maps. This structure is called the Arbuckle. It's just the name. It's like the Himalayas. It's the Arbuckle. It's here in Kansas. And basically, we kind of inject below this dolomite layer that seals in the bio oil, right? And the cool thing is bio oil is very dense, so it sinks relative to water. And so the water table is above this. So that way you're not worried about your oil leaking into your water table that people drink from. And the even cooler thing is bio oil actually solidifies in wells. So I think we'll start on the right. Basically, the right is a temperature versus rate of viscosity increase in centipos per day. Centipos is a unit of viscosity. And basically, the hotter the temperature is, the more quickly it becomes solidified, or it kind of gels. And so there's basically a thermal gradient, a geothermal gradient, right? As you go deeper into the ground, it gets warmer. And you actually don't have to go very far to get 20 or 30 C of warming. And you get an order of magnitude of rate of increase of viscosity by going 20 or 30 C, right? So that's the cool thing. You have this liquid thing you put in, and it kind of moves out for it takes about 48 hours before it begins to gel. And then you just start gelling, right? So now you have this thing that's actually permanently built like in this structure. So you're really not too worried about leakages, right? We do a lot of work to verify that, obviously, but like from a kind of first principles perspective, it's actually pretty compelling that this is not going to leak into the environment, into the water table. Okay, cool. So let's put that all together, right? So what does that actually mean, right? So we've made bio oil, we've transported it to the well, we've injected it, we think it's there permanently, right? Like order tens of thousands of years, even hundreds of thousands of years. It means that we can economically sell bio oil at about $600 a ton. Like I said, we're like kind of losing money, but not actually dramatically, right? It's like actually not terrible. And so you can actually go to this website, charmindustrial.com, and buy carbon offsets, right, for $600 a ton. And it's a permanent removal. We're very confident, in fact, and we have external verifiers that verify that our removals are in fact permanent. And we think that we do have an economic and kind of techno-economic pathway towards getting to about a gigaton annually of CO2 removals. So yeah, I'll stop there and open up for questions.
Okay, thank you very much, Edward. And in that introduction, I had no idea you were Charlie Young's son. Charlie and I have worked together for years since you were a little kid. Great. Okay, questions, great.
Hi, great talk. I was wondering, what is the capacity of all the, like, let's say all the oil wells in the US that have been emptied or dried out?
Sure.
How many gigatons of CO2 could you put in them?
So the like intuitive way to answer that is like almost all of the CO2 in the air came from them. That's the intuitive answer, right?
Yeah.
The actual answer is like about 100. No, I think 1,000 gigatons. That can't be right. I will figure that out. It's dramatically more than we could ever produce. The bio we could produce. It's like, yeah, it's a lot.
Okay.
But I don't know off the top of my head.
Okay, thanks.
We have a lot of hands up. Okay.
Okay.
So Risa, we'll go back and forth between the two sides of the room. Yeah.
Thank you. Great to see you. And this was a lovely talk and it's really exciting work. So I wonder if you could comment on how this relates to all of the other kinds of things people claim to be carbon removal or mitigation. I mean, this seems really better than most things I've heard of. Could you say more about the other kinds of solutions? And
absolutely. So I think the kind of the thing we are fighting in the industry is basically we are pushing really hard for what's called monitoring, reporting, and verification. When you pay for, or anyone pays for removal, you want to be really darn sure that removal happened, right? And so the kind of opposite end of this is like nature-based removals. So basically, if you've ever like purchased a flight and it says like offset the carbon footprint of your flight for $3, right? And it's like, okay, come on, right? And what they're purchasing is they're purchasing nature-based removals, which is they're promising to not cut down a tree that they otherwise would have, right? That's ridiculous. That is absurd, right? For a bunch of reasons. One is that frequently all that does is that the demand for that tree didn't change, right? So all they did is someone went to the next block and cut down another tree. So you have not changed anything. The other thing is we get lots of forest fires, right? So like the thing you didn't cut down is now burnt. So you've also released the CO2, right? So it's all fake, right? Like a report out of Berkeley 3 years ago came out saying that 98% of nature-based carbon removals are fake, right? And so I would encourage you to read that, and I'd also encourage you to never click that button when you buy flights, right? Because you're just throwing away $3 for nothing, right? So what we try to do is we try to be very upfront about what we do, and we have lots of external validators who are actually reputationally motivated more than anything else, because they don't want to put money into an offset that comes out to be fake. One of our competitive advantages is, even compared to other what are called permanent solutions, we're very easy to know what our kind of end-to-end life cycle analysis is. We put amp meters and on all of our electrical inputs. We measure our fuel usage. We know how much biomass we put in. We measure the carbon content of our oil. We measure our transportation usage. And part of, if you go to this website, you can actually see it's the beginnings of it. We're still a startup, but you can actually break down all the hits to what's called the LCA, and you can see it, right? And you can evaluate whether it feels right to you. I am not interested in working at a company that isn't actually making things better, right? Like I've got things better to do, right? But I think our game is to be as transparent as humanly possible. We also, as a policy, take on a very conservative approach to what we sell. So if we have like a 10% error bar on like our carbon content of our bio oil, for example, right? We sell like 1 sigma below the mean, right? So that we can kind of like we hold back, and then as we refine our measurements, because we actually will sell the difference in that when we have confidence that in fact we are hitting that mean or something like that, right? So there's kind of a lot of different ways.
Thank you. So a question from this side. Go ahead. Who has the mic? Seth.
Oh, thanks. I was curious. You said otherwise this corn stalks would be just left on the field and I guess presumably composted.
They just decompose
And
and then release the CO2 in the air as part of the carbon cycle as normal decomposition.
okay, yeah, I was gonna wonder what happens to the soil over time if you're not letting them
Yeah.
decompose.
So that's actually one of the interesting things to Risa's question of like how do we know what we're doing is good, right? And so like if what we did is we removed all the nutrients from the soil and then had to buy commercial fertilizer to put it back on, right? Commercial fertilizers are petroleum based often, right? And so that is something that our company would have incentivized, right? Because if the corn stover decomposes and amends the soil and we remove it, then they have to add extra stuff, right? And so we've actually spent a lot of effort, and part of the research team's group is to understand what that net impact is. And one cool thing is that pyrolysis makes 3 products. It makes bio-oil, which we sequester, syngas, which we're actually beginning to use to burn, to power the process so that we don't need additional inputs to run the process. The third one is biochar. And so that's the solids of the soil, of the plants. And that has a little bit of nitrogen, a lot of the phosphorus, and a lot of the potassium, and then all the heavy metals effectively that are in the soil, like the iron, the manganese, all the things the soil needs. And so you can actually take that biochar and put it back on the field, and you get the majority of the nutrients you need back. And then you can either use chemical fertilizers, or you can use like kind of different farming practices, or you can use like compost and stuff like that to kind of finish it out. And we take that into account in our LCA, our life cycle analysis.
Okay, I'm going to ask a question from online, from Keith Thompson, and it's I think a little bit implicit in the answer to the previous question. But what is the efficiency of CO2 removal? I.e., for every ton that you remove, how much did you release via, for example, gasoline and diesel use? But I think you use your own fuel. But yeah.
Yes. So one of the cool things about biomass is that there's actually 1.6 tons of CO2e removal for every ton of biomass. And that's because you're taking the carbons and you don't have to have the mass of the O's there, right? So you actually get more CO2e removal per ton. So you actually have like every time you process a ton of biomass, you kind of start with a little more than you might think you do. In principle, we should be bio-oil is about 50% to 60% of the total carbon content of the thing you create. So in principle, you should be about 60% efficient. So you should be able to get about it's called 0.7, 0.8 tons of carbon removal for every ton of biomass you put in. That's not where we are right now. We're very early, right? Like when you factor in the diesel and you factor in like our inefficient transportation and all of these things, we're closer to like 25% right now. But there's a couple of, they're not small technical hurdles, but like understandable technical hurdles that should get us to 50%.
Okay. Zeesh, we'll get the prerogative.
What's the path to go from 600 to 100 for CHARM?
Yeah. As you know, first of kind technology is very hard. And so one of the biggest problems for us right now is uptime. So it just breaks. I mean, honestly, it just breaks. It takes a lot of people to run the system right now. So one of my first projects was to automate it. I didn't do a great job. So it is not well automated. So it takes 2 people to run one system at any given time, and we want to run it 24/7. We need to like invert that to have one person run like 10 systems, right? And so that, in addition to automation, means upgrading its safety, and then throughput, right? So for every given system, we're currently running. We want to get to 10 tons per day, but it's much easier to prototype at 1 or 2 tons per day. So we're operating at 1 or 2 tons per day per system, right? And so just imagine you have 5 times the throughput and 1/10 the labor cost, right? You're getting within striking distance.
Okay, so we'll just have time to take one more from that side of the room, one more online, because both of your research mentors have questions. So we'll get both of them, and then we'll move on. Okay, Tom, go ahead.
Oh, wonderful talk. I grew up on a farm, so I have so many questions.
Oh, great. You want a job?
Yes, that's true, actually. But let me just ask one question about the water. If you get to it early, you could recover the water as well. And because I'd worry otherwise you just steam it out and you lose that for no good reason.
Yeah, so water is actually bad for us because it's a thermal sink, right? So you want to operate at pyrolysis happens at like 500 C. So and you effectively have to heat the whole biomass up, right? So we actually deliberately leave it on the field to field dry before we bale it. it's more complicated than that because water catalyzes some oils that we actually want. So the existence of some water actually helps us. So there's like a balance. To be perfectly honest, we're pretty new to that part of the process. So it's like a little bit uncertain, but the drier, the better for us right now is mainly what it is.
That's what I thought. Thanks.
Yeah.
Okay, then Shaolin has a question. How does this compare to turning biomass to carbon and burying? This was astrophysicist Frank Shu's favorite idea.
Yeah. So one of the that's a great idea, right? So I think like you would love to just like take it out of that shredder that I pointed and just like bury it underground, right? That would be like perfect, right? The problem with that is mainly that there's a lot of anaerobic bacteria underground that's actually really good at breaking down like biomass like that. Like oils are much more stable, so they would actually be underground breaking down that biomass, and they would actually make methane, which is 30 times more intense of a greenhouse gas, right? And then you'd also have like methane leaks on fields. So like it's just it doesn't seem like it's a safe pathway for removing carbon dioxide.
Okay, so let's thank our speaker again, and we'll move on to the next one.